We have come to the end of Unit 11, and I usually spend a day in class reviewing all of the different series tests that we've covered. So remember that we've had 10 tests. They all kind of run together. You should have in your notes packet a nice summary of all of the tests that I've given, of all these convergence and divergence tests. It's a nice one-pager with all the tests on there. So let's go through. We're not going to go through all the bells and whistles on each of these problems, but because it's just a little in-class thing, okay? So we wouldn't have time to do all of these problems in class if I was working them all out. But let's go through and let's talk about which test you would use, okay? Which test you would use. So in this first problem, what's a good test to use for that? And sometimes there's not just one answer. Sometimes there are more than one test would work on things, right? So this is one that I can see using the integral test on. I can see using the integral test on this. Why? Because I see that ln of n here. I see that ln of n. And if I let u, if I changed it to x's, I'd have 1 over x log x to the 4th, right? So if I let u be ln of x, then du would be 1 over x, which I have right there. This is a good signal that I'm going to be using the integral test on this one. In class, when I do this review, usually what I'll say is, if there's one you want me to do, tell me, and we'll do it. And this is one that kids usually say, oh, can we review that integral test again? And so let's go ahead and do that. So first of all, I write it as a function with x's. And I have to say that this function is positive, continuous, and decreasing. And after a quick examination, I see that that is true for these values of n. Okay? All right, then I take the integral from 3 to infinity, because those are the values on my series. All right, come off to the side, do a little u sub. U is natural log x, so du is 1 over x dx. And 1 over x dx I have sitting right there. So that's my du. So what I have left is the integral of 1 over u to the 4th du, right? Or u to the negative 4 du. My boundaries, if I change them to u boundaries, I'll have natural log of 3 on the bottom, and I'll have infinity on top, because natural log of infinity is infinity. Okay? All right. So now antiderivative time. So the antiderivative of u to the negative 4 is u to the negative 3 divided by negative 3. So that's negative 1 over 3u cubed, right? 1 over 3u cubed, negative. And then we're taking that from natural log of 3 to infinity, but we don't write infinity. Make that a b, and we say limit as b goes to infinity. Right? Now put b in for u and let b go to infinity. And when we do that, we get 0. Minus, now put ln of 3 in. Now put ln of 3 in for u. And we'll get negative 1 over 3 ln of 3 cubed, like that. Did this converge or diverge? Well, this converged. because we did not get infinity. Therefore, the series converges by integral test. Okay? The integral test is a bit of a pain, and I get that. Okay? Especially compared to some of the other quick tests that we have. But be prepared to do it if you need to. Okay? So this one would converge by integral test. And hopefully you've done enough of that in your homework and stuff to where that's obvious that you would use the integral test on that one. Okay? What about number 2? What is that? What's happening over there? Well, that is a p series. What does p equal there? P is equal to 3 plus a third. 3 plus a third, which is 10/3, which is greater than 1. The denominator is big. That it's bigger than 1. The exponent is bigger than 1. So the denominator is big, so the denominator is heavy. It's pulling it down to the x-axis fast. So this converges by p-series test. Okay? All right. Look at number 3. Well, for this one, I see Big Mama right there. Where is she? She's in the denominator. She's pulling that bottom down to the x-axis really, really fast. Okay? So that I know this is going to converge. What test could we use to prove it? What test could we use to prove that? It's a factorial, so I would use the ratio test. Okay? All right, what about this one? The numerators are the same. We have a minus and a plus. We have n's in the bottom. This is telescoping. And since it's telescoping, I know it's converging. Okay. So far we've had 4 converging. Okay. What about this one? What about this one? This is one, you guys, if you use the ratio test or the root test, you would get 1 for the limit. And so you'd have to go and use a different test. Okay? So this one I would use the alternating series test on. It's alternating in sign. Is it decreasing in magnitude to 0? Yes, it is. So this will converge by alternating series test. Okay? What about this one? What about that one? You could use the root test, you could use the ratio test, or you can see that this is a geometric series and use the geometric series test. Either one. Okay? So if you see that geo series, what would R be? What would R be here? R would be E over 3, which is less than 1 because E is about 2.7 something, right? So that's less than 1. If R is less than 1, then the series absolute value of R is less than 1. So the series converges by geo series test. If you did the ratio or root test, you would also get E over 3, okay? Which is still less than 1, so you could say it converged by ratio test or by root test, okay? What about this one? Well, we would use the limit comparison test, and I would compare with what? I would compare that with 1 over n squared. Only the biggest degree on top and the biggest degree on the bottom, and you simplify. So compare with this, what's it going to do? It's going to converge. And that would be limit comparison test. Okay? Limit comparison test. And remember, you need the conditions for that, and you need to show me the work. But that's what it'll do. It'll converge by limit comparison test, because this one is a converging P. Right? What about this one? I would use the root test on this. It's complicated. It's complicated. I could also use the alternating series test on this. That would work as well. I could also use the ratio test on that. That would work. So any of those would work. I would use the root test. And I see this n up on top, and so I know that that limit would be 1, right? Here's another n on the bottom. That limit will be 1. The only thing that I'm going to be using is this 1 over e, right? So when I do that limit, I will get 1 over e, which is less than 1. So this converges by root test. What about this one? Can't use the ratio or root test on this one. Won't work. This one we need to use a comparison test. I would compare it with 1 over n squared, which converges. And I could either use the limit comparison test or the direct comparison test in this one. Remember the limit comparison test, that's the one where you need the limit to be finite and positive. Okay? Number 10. Number 10. What is this? What is this? I could use the root test. I could use the root test. Or I can use the fact that the limit as n goes to infinity of this. Oh, you know what? I cannot use the root test. I would get 1 for my answer, and that's not going to work. The limit as n goes to infinity of that, I recognize as e squared. First thing on your formula chart, right? So, which is not 0. It's not 0. So this diverges by nth term test. Our very first test that we did. What would you use in number 11? I would use the integral test. Again, I see an ln of n and I see a 1 over n, so integral test. This will end up diverging by integral test. What about this one? Well, it's alternating, and it behaves like an alternating 1 over n cubed, doesn't it? So it will definitely converge by alternating series test. Since the non-alternating converged, it would be 1 over n cubed. The non-alternating converges, so this is actually absolute convergence. What about this one? Gosh, what a mess. What a mess. All right. Well, it is a total mess. I would use the root test. Do you know what this one does? What does this one do? The n will not matter because that limit will be 1. When you take the nth root of n, it's 1. So we'll be left with these 4 to the n, e to the n, 2 to the n things. So it will be, the limit will be 4 divided by e times 2. Is e times 2 greater than 4 or less than 4? It's bigger than 4, right? Because e is 2.7 something. So this limit will be less than 1, so this will make it converge. Could also use the ratio test on that. What about number 14? I see Big Mama in the house, and she's plopped up on top of that fraction. What's she going to do? She's going to make this diverge. This is definitely diverging. Which test would you use? Ratio or root? Either one. Okay. Conditional versus absolute, or does it diverge? Okay. What about this one? This one. Well, it's alternating, decreasing in magnitude to 0, so it definitely converges. So if it's not alternating, does that converge or diverge? If it's not alternating, this behaves like 1 over n cubed, which converges. So even the non-alternating converged, so the alternating will absolutely converge. What about this one? Well, it's alternating in sign, decreasing in magnitude to 0, so it is converging. Okay? If it's not alternating, does that converge? No, it does not. It behaves like 1 over n, which diverges. So this one is conditional. What about this one? It is alternating in sign. Is it decreasing in magnitude to 0? Is the limit 0? I see something with n, so I have to be careful up here. Pi to the n over 3 to the n. The plus 4 won't matter as n goes to infinity. The limit as n goes to infinity of this, pi is bigger than 3. So this is not 0. This diverges by nth term test. Okay. On the back side of that sheet, what must you state before using the integral test? You must state that your function is positive, continuous, decreasing. What must you state before using the comparison tests? You must state that both a sub n is greater than or equal to 0 and b sub n is greater than or equal to 0 for n greater than or equal to whatever the bottom value of your sigma is, whatever n is starting at. Okay? What must you state before using the alternating series remainder theorem? You must say that the terms are alternating in sign and decreasing in magnitude to 0. You must state that. Otherwise, we don't even know if the thing converges. What must be true for an alternating series to converge? Well, terms are alternating in sign and decreasing in magnitude to 0. Same thing. These are the same thing. You cannot use your alternating series remainder theorem unless you state that your series is converging, and this is how you state it. Okay? Which are the only types of series we can find the sum of for right now? Telescoping and geometric. Remember, for geometric, it's your first term divided by 1 minus r. How do you find the value of a converging geometric series? The first term divided by 1 minus r. How do you find the value of a telescoping series? You write out terms, see what cancels, and what you keep. And just add together what you keep. How do you determine if a sequence converges or diverges? Not a series, but a sequence. Take the limit as n goes to infinity of your a sub n formula. If you get a number, the sequence converges. It does not have to be 0. If you get a number, then the sequence converges. If you don't get a number, if you don't get a single number, then the sequence diverges. Okay? If a series is larger than a known diverging series, does it converge or diverge? Well, it diverges. Which test is that? That's the direct comparison test. Why do we even care if a series converges or diverges? Why do we care? Well, this is leading up to our next unit, you guys. And in our next unit, we will be able to use series to evaluate integrals that we have not been able to evaluate yet. Like this integral. Or this integral. Things that we cannot use a u sub on, we can use series to find out what these are. Okay? Plus, it just is a way to stretch our brains and learn about something in calculus that is a little different. It just allows us to use our brain in a different way. So, another great reason to study them. Okay? Alright. So, test. Probably next time I see you will be the test. So, study, ask questions, and we'll do well on the test. Alright.